All right, so in the interest of time, we're going to go ahead and jump ahead to the oscillations in the power grid. As you can see up here, we do have a pretty full agenda, and we're going to do our best to stick to our time limit and hopefully finish fast enough to get some questions in from the audience. I'll be doing a quick background. Kellen will cover some real case studies. Lew will discuss security and PMUs. And finally, Parimal will round out today's discussion with impacts and next steps. So first, we're going to go over what's called small signal stability. And to help me try to explain this, I tend to use the tandem bike analogy. You'll see the people in red are pedaling. Those are the generators. Meanwhile, the people in blue are feet up being carried by the generation. They represent the load or demand. They're not pedaling. If you've heard this analogy before, then you already know there's a variety of issues that can cause destabilization of the bike or cause a bike crash. One example is that a person pedaling has slippery shoes, a failure at a power station, and eventually during the ride, their shoe slips off the pedal. The generator is shut down. What happens? Well, the tension on the bike chain drops, a voltage dip on the grid, and there's a risk of the pedaler hurting themselves since the pedals keep moving whether they're pedaling or not, especially on a tandem bike. To compensate, the other pedalers need to keep up the work, otherwise the velocity will drop and lead to a crash. And it's tricky for the original person or generator to get back their foot on the pedal because like a generator has to reconnect, their frequencies need to match. The same issue can occur if another blue rider jumps on the bike, another voltage dip, or if a blue rider jumps off the bike in a voltage peak. At the end of the day, we want to make sure the frequency, the velocity of the bike, and the voltage level, the tension on the chain, remains steady. Small signal stability is the ability of the system to maintain stability after the smallest disturbances in the system, like those load changes, the line switching, the blue riders jumping on and off, that can also manifest as the inability of the system to return to a steady state after a severe disturbance in the system and demonstrates sustained low damped oscillations, aka abnormalities, following the clearance of the fault. So all that's to say that in our analogy, it's like the pedaler can't get their foot back on the bike, and the other red pedalers are working hard to match the speed needed to make up for the loss of the one. And if these abnormalities persist over time, and the original pedaler just can't catch that pedal again, and the remaining pedalers just can't make up the speed, there is a risk for the grid and the bike to experience instability. So from our example with the tandem bike and the pedaler who missed the pedal, we like to say that's the disturbance. Now, what keeps the bike from crashing immediately is the inertia and the damping parameters. You already know inertia, an object in motion tends to stay in motion, and while damping refers to the physics of the conventional machines, plants that have rotating parts. Damping torque is rotational force that opposes the oscillations of the machine's rotor, or it's the bike wheels that keep turning even when you stop pedaling, which helps to stabilize quickly after a disturbance. On the power grid, we have devices called FACTS, the Flexible AC Transmission System devices, and those enhance the controllability and power transfer capability of AC transmission systems by rapidly managing real and reactive power flow. So for example, that would be an SVC, a static VAR compensator, which can help restore stability. When it comes to oscillations, conventional machines, like the one shown in the top left corner, exhibit oscillations by physically rotating. Meanwhile, with IBRs, they create oscillations or waves by electronic algorithms. No momentum, no inertia, just nav. You can also think of damping as a way to push down on the amplitude of the disturbance's oscillations. On the system, you want about 3% damping available to push down the crazy waves to make them more normal. If you don't have enough damping, not enough push down, then the disturbance spirals out of control, getting bigger and bigger until it crashes. Small signal stability analysis requires the same data that would be needed for transient stability or dynamic analysis. Basically, we need models for all the dynamic components in the system, like conventional machines, FACTS devices, dynamic loads, IBRs. Any small signal stability analysis tool uses these dynamic models and the power flow case to create something known as a state matrix. The elements of the state matrix are direct functions of the parameters of the dynamic devices, such as the damping and inertia parameters of conventional machines. The tools specialize in eigendecomposition, which is basically taking a complex state matrix and bringing it down into simpler components called eigenvalues and eigenvectors. Small signal stability is characterized by the term known as modes of the system, with each mode comprised of different frequency and damping. This involves the rate of occurrence and magnitude of the anomalies identified. So depending on a mode's frequency, its damping and participation of the devices in that mode, a mode can be critical or not critical related to system stability. So basically, to break that down, what we have are called local modes of oscillations. So these are small, as it implies, local generator, oscillating against the rest of the system. This is a single biker who is getting out of sync with the rest of the bike, pedaling a little slower, maybe they're getting tired. And in reality, this mode has a limited geographic extent, usually 50 to 100 miles. So a grid example would be that a generator at a power plant oscillates against another generator at the same plant or against the local transmission network. We also have intra-plant modes of oscillations. This time it's multiple pedalers in the same part of the bike are starting to get tired and get out of sync. And finally, we have what's called inter-area modes. And like it sounds, it's the entire area now oscillating against another area. A fleet of tandem bikers are in a parade, and suddenly some of the bikers in the front left area just start getting tired, and multiple generators moving within the area. These oscillations span large geographical distances, hundreds of miles, and are influenced by those transmission line impedances and tie line power transfers. So these modes typically arise from the bulk power transfer across weak tie lines connecting different regions. And when the power transfer strength or tie line strength decreases, these modes become poorly damped, and again, they spiral or oscillate out of control. So you may be wondering, how do we dampen these oscillations? Is there a difference between how we handle them depending on what mode they are? So for the local modes, a single properly tuned PSS can effectively damp local oscillations because, again, it's usually one generator or a few closely located machines. Meanwhile, if we're looking at the inter-area mode damping, that requires coordinated control of multiple PSSs because now we have multiple generators that can be across different areas, and the added complication that individual PSS actions can actually reinforce or cancel each other out, depending on the relative participation in the inter-area mode. So here we're going to cover system response types and their detection methods. You'll see the oscillation system response types broken out in that graph in the middle: ambient, transient, and forced. An ambient response is the response of the system to small random changes. So this would be load, line switching, or generator controls. And as you can see on the left and the middle of the graph, they're small, the amplitudes are short. So ambient data-based oscillation detection, so that analyzes the small signal stability in normal operating conditions without any requirement for a disturbance to happen. So that would basically be the continuous monitoring method. You don't need a full-on disturbance to kickstart the detection, and it's great at tracking slow, creeping changes in the system conditions. However, this does mean that we lose out on accuracy, and it requires the longer data windows. So think of it as 10 to 20 minute windows you now have to analyze. And as you can guess, it's also more sensitive to noise. So that takes us now to the transient response. Transient response is the grid right after a sudden disturbance. So that's when the pedaler's foot slips off the bike and the team felt the immediate loss of power. Maybe the bike even tipped a bit in the jostling. On the grid, that would be a fault or a line or generator trip, or even a load tripping offline. Sometimes you might also refer to this as the ring down. So remember, this doesn't always mean the bike is going to crash or the system won't recover when you have this. So for the ring down oscillation detection, so that basically involves analyzing the small signal stability after a major disturbance. So the advantage here is that it has high accuracy in the frequency and damping estimation, and it has a faster computation time because you have shorter data windows to actually look at. It's also not reliant on system models being available and accurate. However, it does require an actual disturbance to be present, so because it's not continuously monitoring, and it means that there's less data frequently available. You may have noticed that I did skip over the last wave on that graph, the forced response. This gets its own slide to itself. It's a separate category. So when ambient and transient oscillations are called natural responses, forced oscillations fall into their own category of forced response. Creative titling. The forced response is the response of the system associated with an external input, a rogue input. This could be something like malfunctioning equipment, unintentional behavior stemming from control systems that need to have been better coordinated, and it can come from any generation type, IBRs and conventional generation included. It can even come from a poorly tuned PSS. And unlike transient oscillations, these oscillations typically persist until the forcing input, the cause, disappears or is removed from the system. So to compare that to transient oscillations are kind of like a pendulum that swings until it stops due to the air resistance. Meanwhile, forced oscillations is like a child being pushed on a swing, maintaining their motion until you stop pushing. Detection-wise, forced oscillations are purely based on measurement data. Tracking with PMUs are critical to this. If forced oscillations are not suppressed or ended, they can cause equipment fatigue, damage to rotor shafts, poor power quality, and even generator tripping. And next up, we're going to have Kellen present on some case studies. Kellen, when you're ready.
Yep, can you hear me?
You just fine.
All right, perfect. Good afternoon, everyone. My name is Kellen Phillips. I'm Principal Analyst here at Reliability First. I'm going to share a couple case studies with you this afternoon from some real events on the North American power grid. I'll include the timeline of each case, some lessons learned, and if you haven't already, please join in Slido to answer some questions. All right, let's set the scene for the first one. It's August in the Northwest, and we're experiencing a heat wave with high demand. Oregon starts to see some line strip, several lines over the course of 2 hours. Then at 15:42 in the afternoon, a large line sags into trees. I think you can already tell something bad is coming. Okay, on Slido, if you'd like, what type of system response do you think is going to occur? Feel free to answer as I keep going. Within minutes of that fourth line tripping, there are more failures, including a second line grounding to a tree in Vancouver, Washington. And then 13 turbines trip offline at the McNary Dam in Oregon. The loss of the dam's reactive power made the grid susceptible to voltage frequency oscillations, and a low frequency oscillation occurred, which began a chain of events, a cascading failure, which ultimately resulted in a blackout with 7.5 million customers losing power across 7 U.S. states, 2 Canadian provinces, and a portion of Mexico. It cost an estimated $2 billion and led to the development and deployment of new sensor technology like synchrophasors to better identify and mitigate power swings before they lead to another widespread outage. This example is from August 10, 1996, known as the Western U.S. Blackout. As we know from Slido, this was a natural oscillation, specifically about 0.25 hertz, which became negatively damped. Its amplitude grew and grew rather than fading after each disturbance. The 1996 event reinforced the importance of monitoring grid dynamics and led to the development and widespread deployment of advanced sensor technology, such as synchrophasors and mode meter software to identify and mitigate unstable power swings before they cause widespread outages. Let's do another one. It's another hot August day, and this time we're in the Eastern interconnection. The air conditioners in northern Ohio and eastern Michigan are cranking. A few generators are forced out of service, but we're in the green and forecasts say we're good to go. The state estimator tool, which operators use to monitor the system, gets inaccurate input data, which renders the tool ineffective. For those less familiar, the state estimator tool feeds into the RTCA, or real-time contingency analysis, the if this happens, what happens next? For example, if this line trips, where do the remaining megawatts go, and does it overload any other lines? What if this generator trips, and so on and so forth. Whether there's a big change in the power system, the operators will run the tool to analyze those contingencies. The issue here is that the state estimator is down and effectively the RTCA is down with it. The operators can't see what potential outages could happen, potential overloads, and so on. In addition to the state estimator tool being down, voltage on the system was low and there wasn't enough reactive power. Capacitor banks are used to help balance this, and 4 of them were out of service on this day. So operators chose to overexcite nearby power plants, basically pushing units to their limits to get more reactive power. This was the case with a coal-fired plant on Lake Erie, East Lake Unit 5. At 1:31, East Lake 5 was pushed too hard and the unit tripped offline. This resulted in losing more voltage control and pushing other plants even harder. About 45 minutes later, the utilities control room started experiencing a series of computer failures. The alarms and logging system failed. Think of it as if you're driving on a country road and your fuel gauge is stuck showing full, not realizing you're nearly out of gas. With the state estimator out of service, East Lake 5 offline, and the control room computers failing, the grid in the area was very vulnerable. Now, when you carry more current across the lines, they heat up and start sagging. Couple that with a hot day, and they're really sagging. At 3:05, several 345 kV lines sag into overgrown trees and trip offline. Back in the control room, the operators don't see this. Remember, they're still driving with the broken fuel gauge. These lines tripping means the power has to go somewhere else, so it overwhelms the 138 kV system. And time for a Slido question. What mode does this sound like? Put your guesses in, and it should tell you the answer after you guess. And you'll also see there's a bonus question. See if you can name this blackout. At 4:06, all the line losses and surging power had come to a head at the Star 345 kV line, which was suddenly loaded at 120% of its rated capacity, therefore causing its relays to assume a fault had occurred and tripped the line. After Star tripped, within 6 minutes, low voltages, big power swings, and accelerated line tripping would cause separations and blackout within the eastern interconnection. It happened so fast that operators had no opportunity to mitigate the cascade, and the grid collapsed across the Northeast Canada, affecting 50 million people across 8 states and Ontario, Canada. The blackout stranded subways, halted traffic, closed businesses, and disrupted air travel, costing us here in the U.S. between $4 and $10 billion. And yes, for those of you who got it in the bonus Slido, this was the August 2003 Northeast blackout. Up here we have a simulation of the oscillations of the grid along with the frequency swings shown in the map. You can really see how each trip brought us closer and closer to collapse, and really how fragile the grid can be. A blackout from a few trees and a computer bug. If you haven't seen it already, RF released a 20 years of progress video looking back at the 2003 blackout, which you can check out on YouTube. Let's do one more. This time, it's a cold Friday in January, but fortunately for us, we're down in Florida. Not a great picture. Anyway, as we said, it's a Friday in January, and for this event, we're in Florida. Really early in the morning, an oscillation starts. You'll also notice that we have added seconds to the time, and that's because 25 seconds later, the oscillation continues and is observed across the entire eastern interconnection. Jump into Slido. What do you think happens next? At 9:02, a plant operator manually takes a combined cycle unit in Florida offline and solves the oscillation issue, after it had persisted for 18 minutes. And another Slido. What seems different about this event compared to the last two we went over? That was a more recent event, January 11th, 2019. As you can see here, the oscillation starts in Florida. Now, what caused it? A failed potential transformer, also known as a PT connection, and an erroneous voltage measurement in the controller meant that the controller thought there was an imbalance, so it shut valves, waited 4 seconds, reopened them. The controller still thought there was an imbalance, so it closed them, waited 4 seconds, and reopened, then closed, and so on and so on. This meant the steam turbine at the combined cycle plant oscillated for about 18 minutes until a local plant operator removed the unit from service. That open close was cyclical every 4 seconds and resulted in an oscillation at the perfect frequency to be felt across the entire interconnection. All the way in New England, they saw power swings of about 50 megawatts. The plant itself had oscillations around 200 megawatts peak to peak, for those wondering. The good news, the oscillation ended rather quickly. Operators identified the oscillations quickly using SCADA data and grid monitoring tools and PMU measurements, which Lew will talk about more in a second. It turned out there was failed wiring in the PT cabinet at the plant, and there were faulty valves, the ones that kept opening and closing, meaning the plant was offline for multiple weeks for repairs following this event. To wrap up the case study section, the key to all events we went over is that we have monitoring and damping technologies to detect, locate, and mitigate these oscillation events in real time. That means PMUs and PSS, or power system stabilizers. That concludes my section, so I'll turn it over to Lew to go over PMUs and synchrophasors. Thank you.
Thank you, Kellen. You're used to normally sampling transmission or generation data on a 2 or 4 second basis for SCADA. Synchrophasors sample it much faster. Synchrophasors are actually the measurements, and they are accurate measurements and very precisely time-stamped using GPS traceable time signatures. There are usually, as opposed to 2 to 4 seconds per sample, you typically have either 30 or 60 samples per second. So much faster. Therefore, you get a much better picture of what's going on the grid. Now, this creates a challenge because that's a lot of data. So you have to get that data from the phasor measurement unit, or PMU, usually through a phasor data concentrator, or PDC, back to the system that's going to be using it. So this provides wide area, possibly, depending on where your synchrophasors are, your phasor measurement units are installed. But typically, you've got a wide area monitoring effect because you have a lot of these PMUs scattered around. At last count I saw, I think there were 700 and some. Let's go to the next slide, please. So in the activity, we're actively working on synchrophasors in the ERO. The Synchronized Measurement Working Group is working on a white paper for integrating PMU data into real-time operations. And the Security Working Group, a subgroup of that, is working on a security guideline for incorporating that data into real-time operations and what the security impacts of that will be. Because if PMU data is used for real-time operations, it stands a good chance of bringing the phasor measurement unit itself into SIP scope. Now, typically these PMUs reside in things like relays, so that there shouldn't be much change to your SIP posture. Let's go to the next slide. And that was my That was my part of the presentation. Courtney, back to you.
Thanks, Lew. So what can this PMU oscillation analysis look like? So I'm going to pull an example directly from NERC's document shown up here, which includes an example from a utility who uses PMU-based applications for online oscillation analysis and offline event studies. So they have field PMU units stream high sampling data to a data repository, and that data repository system will then dispatch PMU data streams to a phasor point, in which real-time monitoring is enabled, and alarms are generated and transmitted to the EMS. So as of the release of this paper, the utility deployed close to 400 PMUs across the Eastern interconnection. So with that large amount of data accumulated, real-time oscillation event detection on frequency and active power was developed and deployed in control rooms to enhance situational awareness. So basically, the report describes that the utility took advantage of the high sampling rate of PMUs, like Lew mentioned, to visualize and document the system dynamics in phasor point. The purpose of developing this event detection mechanism was to help control room personnel quickly identify harmful oscillations from the common system variations. So with the online modal decomposition in phasor point, the system dynamics can be decomposed in real time. So basically using that oscillation magnitude and decay time as two metrics to measure the severity of the oscillation. Basically, the bigger the magnitude and the longer the decay time, the more severe the oscillation would be. The reference document states that while it's preferred to avoid alarms on the small, quickly damped oscillations, the lingering ones with the big swings are supposed to be caught by the operators as fast as possible. So for timing purposes, we don't have time to go over all the technical methodologies they reference in this document, but it is available to read online in full on NERC's website, so please feel free to check it out or reach out to us afterwards if you want a deeper dive on oscillations in general. So in order to enhance the situational awareness for the control rooms, this company, they automatically generate a PDF file of the daily PMU report, which is then archived in an internal shared folder. That report includes information on the system average frequency, summaries of oscillation events, detailed event charts, and PMU data quality statistics, and it actually even lists the poor quality PMUs that are in need of maintenance. Now, next up, we're going to have Parimal present on some of the current and future impacts on oscillations. Parimal, when you're ready.
Thank you, Courtney. Good afternoon, everyone. Can you hear me?
Sound great.
Perfect. Good afternoon, everyone. My name is Parimal. I work in the engineering and system performance team at RF. And today I'm going to talk about some current technologies technologies and aspects of some of the new technologies that are going to have a significant impact on small signal stability and oscillatory behavior of the grid going forward. So the first thing I'll talk about is the inverter-based resources, or IBRs. And then I'll move on to, newly talked about large loads and data centers. And finally, I'll talk about HVDC lines. There are high voltage DC lines that are being proposed as an alternative to high voltage AC lines in the North American electric grid. So yeah, Courtney, next slide. So I don't see the text, maybe, yeah. So the first aspect, how the IBRs really impact the small signal stability of the electric grid, is through inertia. So traditionally in the electric grids, the inertia was provided through conventional synchronous machines that had a physical rotating mass. However, most of the IBRs that have been installed today on the field are mostly based on the grid following technology that inherently does not have the capability to provide inertia to the grid. The newly proposed grid forming technology does have capability to emulate or provide synthetic inertia, but it requires the IBRs to have active power headroom in order to provide that feature or capability. So that's again restrictive in some form or aspect. So essentially what will happen is inertia has a major impact through how it's modeled in the state matrix and the small signal stability analysis. Inertia forms a major aspect of how it impacts the frequency band and damping of inter-area oscillations. So essentially, as we have more IBR penetration going forward, as a replacement of the inertia, it will have a significant impact on altering these inter-area modes through in their damping and frequency bands. Next slide, Courtney. So other than inertia, there are several other newly found behavior that these IBRs reflect in the system that have not been seen in the traditional electric grid. So before I move into the details of these phenomena, I want to talk about a couple of items. First thing is SCR, that's called the short circuit ratio. It's essentially a representation of the strength of the electric grid, and it basically tells how stiff the voltage is in that portion of the grid. And the other item I want to talk about is PLL. That's called as phase lock loop. It's a specific device that's installed on the grid following IBRs that essentially tracks the parameters of the grid that are essentially utilized then for the control algorithms that are part of the grid following IBR technology. I'll start with the control to control interaction. So what happens is in an IBR plant, there are numerous IBRs, which means the plant might have 100 solar panels or thousands of solar panels, and each panel has its own local controller. And then there's a plant-wide controller called a power plant controller. So under certain conditions, if these controllers, that is the plant-wide controller and these local controllers, if they are not tuned properly, they can have interactions with each other, and that can result in oscillations. So a single IBR plant can demonstrate something known as control to control interactions, where different controllers that operate on different time scales can interact if not properly tuned and trigger oscillations. The second phenomena is control to grid interactions. In this type of phenomena, what happens is there is essentially resonance that happens between the grid impedance and the impedance of the IBR plant. Some of you folks might have already heard about a phenomenon named subsynchronous resonance or subsynchronous control interactions that are specific to IBR plants. So essentially, a resonance occurs between the grid and the IBR, and that results in oscillations being injected into the grid. And then another phenomena is multi-IBR interaction, where different IBR plants that are in close vicinity to each other interact, and that essentially triggers oscillations into the grid. And this has been observed specifically predominantly under weak grid conditions where the grid strength is low. A good example of this type of phenomena is what has been seen in the Panhandle area of Texas, where which is predominantly IBR generation there. And what happens is it's a weaker portion of the Texas interconnection, and multiple IBRs that are closely installed to each other, they exhibit interactions and have shown to inject oscillations into the system. So that's another phenomena that has been noticed in weaker portion of the electric grid. And reduced damping I already talked about. This is predominantly a function of inertia getting replaced in the system, and that results in reduced damping of these oscillations. And there's a snapshot on the left that is an example from AEMO in Australia. Basically, what happened in this particular event is under weak grid conditions, the PLL of grid following IBRs that were installed in that region, they basically demonstrated instability, and that resulted in oscillatory behavior, and multiple IBRs in that general region, they all started oscillating, and that's how these oscillations were observed in the transmission level voltages in that region in Australia. So next slide, Courtney. So moving on to large loads, this snapshot on this slide is basically a capture of the training profile of an AI data center load sized at rated at 50 megawatts. So as has been seen in several data center profiles and also reported in recently published NERC large load white paper, working group white papers, these AI data center loads tend to ramp up and down extremely quickly within few seconds, ramping up and down between training and then saving checkpoint progress. And these ramp up, ramp down spikes can be several hundred megawatts in size within a few seconds. So if you look to the slide on the snapshot on the right, the ramp up that's on the leftmost picture is from 0.15 per unit on a 50 megawatt base, which is around 7.5 megawatt, to around 0.6 per unit, which is around 30 megawatts. So this power ramp up goes from 7.5 megawatt to 30 megawatts in a matter of few seconds, less than 2 seconds essentially. So this is a 50 megawatt data center. So imagine if it was a 500 megawatt data center, imagine the spike that or this ramp up profile that the grid would have seen. So yeah, this essentially what this how this matters for oscillatory stability or small signal stability is essentially it will induce forced oscillations into the grid because of this extremely rapid ramp up ramp down profile, and that can cause if grid already has a poorly damped inter-area mode, this forced oscillation can worsen that inter-area mode and result in oscillatory instability. So next slide, please. So essentially, the way large load impact the oscillatory stability is can you click, Courtney, to have all the three? So once more, yeah. So the way the way large load impact the oscillatory stability is, as I mentioned, through forced oscillations. And if these large loads are closer to generators that have a high modal participation in an inter-area mode, what might happen is these large loads can amplify those inter-area oscillations and destabilize the electric grid. These large power swings that are happening as a result of these ramp up, ramp down profiles can also cause relay miss operations, which in turn can trigger cascading in the system and again cause a major instability event in the electric grid. And also these oscillations can cover a large area, as is well known. Inter-area oscillations typically, if they are poorly damped, they can be seen across a larger footprint. So if these large loads are closer to areas that have a poorly damped inter-area oscillation mode, then these oscillations can be seen over a very large area. So next slide, please. So recently, there have been talks about setting oscillation limits for these large loads in terms of how much, in terms of the magnitude of the megawatt swings, how much is allowed. So recently, ERCOT has proposed a limit in terms of how much megawatt variation they will allow in order to control or kind of take care of these the risk of these loads inducing forced oscillations into the system. And then ERCOT also observed in a case study or an event analysis that PMUs that were installed in the ERCOT footprint or Texas footprint showed a forced oscillation being induced into the system, basically with a variation of 15 to 20 megawatts at 7.5 hertz. But under further investigation using a digital fault recorder, it was observed that the actual oscillation was sized at 50 megawatt amplitude at 23 hertz frequency. So this was also reported in discussed in one of the recently published NERC large load working group white papers. So there is a need of utilizing high resolution point of wave measurements in order to really track and kind of control these forced oscillations being triggered by these large load behaviors. So next slide, please, Kurt. And this is the last technology that I'm going to talk about today, which is HVDC lines, high voltage DC lines. So essentially, they have been proposed as an alternative to AC lines because they have very low losses and they have been used to interconnect different interconnections. So, however, these HVDC lines are also based on control algorithms, and they also use the PLL, which is the phase lock loop, to track the parameters of the grid in order to run their controls. And as has been discussed for IBRs in the previous slide, PLLs under weak grid conditions can excite low frequency oscillations in the system. Also, HVDC controls can interact with nearby IBR controls if they are in a region that has a significant IBR penetration and can introduce new poorly damped oscillatory modes. HVDC lines also have demonstrated converter-driven impedance resonance-based oscillatory behavior in a lot of offshore wind farms. HVDC lines have been used to transport the power and into the electric grid, and those HVDC lines have shown to demonstrate supersynchronous oscillations, which is essentially, again, resonance between the wind farm, the offshore wind farm, and the electric grid. And they also basically, it's very similar to subsynchronous resonance kind of a phenomena. And it's basically grid resonating against the wind farm. And HVDC lines have also demonstrated that oscillatory behavior. And then in the end, essentially, HVDC controls can be tuned and need to be tuned to stabilize these oscillations. So these oscillations can be stabilized, but it involves tuning these controls that are installed on the HVDC lines. So yeah, next slide, please, Courtney. Yeah, so please share something new that you have learned today from our presentation, and I will look forward to your comments. And yep, please share on the Slido. And next slide. So presently, actually, as part of a lot of analysis that we are performing, there are a lot of discussions on frequency studies, basically analyzing historical events and analyzing the frequency and behavior in terms of the frequency in nadir that was seen, as well as any oscillatory behavior that was seen, and trying to run planning studies based off those oscillatory events to validate it through our planning studies. Then in the future, there's a lot of analysis or work that is being going on running small signal stability in under weak grids, weak grid conditions. So that might a lot of analysis that has been performed provides a lot of direction into a need for EMT or electromagnetic transient analysis, because traditional analysis based on phasor domain tools such as PSSC or PSLF might be lacking adequate granularity to represent a lot of these newly observed oscillatory events that are being triggered through either IBRs or large loads or HVDC lines. So there's a lot of push towards using and need towards using the EMT analysis for really observing a lot of these newly demonstrated oscillatory events on the electric grid. So that's pretty much it from me, and thanks a lot for listening to us. And yeah, Courtney, back to you.
Thanks, Parimal. Unfortunately, due to the time